It is a great honor to be able to speak here via this online platform. My name is Kazuhide Ito, Kyushu University, Japan. And here I would like to deliver the talk about the current status of the development of computer-simulated person or in silico human model in terms of airborne transmission analysis in indoor environment from the activities of our research group. In case of conventional studies on health risk in indoor environments, for example, airborne transmission, virus reagent droplet exposure, and corresponding infection risk, in vivo and in vitro studies are usually applied. As you well know, the in vivo and in vitro approaches have very rigorous restrictions on their implementation from the point of medical ethics and animal protection. In contrast, in silico approach is expected to be a promising technique to replace or to complement in vivo and in vitro studies. In this talk, I would like to introduce the development outline of an in silico human model for health risk assessment intended for the application to indoor environmental design. In indoor environments, transient and non-uniform contaminant concentration distributions are generally formed. Therefore, in order to accurately predict the virus reagent droplet concentration for inhalation exposure and respiratory infections and evaluate the resultant viral replication, it is necessary to perform integrated transient injury safety and in silico human model analysis. This slide represents the development of a computer-simulated person, CSP, premised on the application of safety analysis undertaken since the 1990s. To the best of my knowledge, Murakami and Kato's research group at University of Tokyo proposed the first CSP that reproduced the human body geometry with safety analysis. The CSP reported in 2003 by Dr. Dan Sorensen at the Technical University of Denmark is a very important achievement as the development of a digital twin model that accurately reproduced the experimental thermal mannequin. Since then, various researchers have proposed CSPs and reported integrated numerical analysis method with thermoregulation models for skin surface temperature control and safety analysis. Our research group is also working on the development of new thermoregulation models and closing models for skin surface temperature control. Concerning the development of numerical models for the assessment of inhalation exposure and respiratory infection, the research group of Dr. Kiao Insabon at MIT University and the research group of Dr. Yufan, Oklahoma State University, have reported excellent research results so far. However, the development of a CSP for evaluating inhalation and thermal exposure and resultant health risk in indoor environment is still limited. In this presentation, I will introduce our CSP with a respiratory system for inhalation exposure analysis. In order to perform detailed numerical analysis of airborne transmission in the indoor environment, generally, we need to develop numerical models in 4 steps as shown in this slide. Firstly, it is necessary to precisely model the generation of virus reagent droplet in the respiratory system. Secondly, we need to understand and model the transport mechanisms from virus reagent droplet generation by coughing and sneezing to the mucosal epithelial tissue surfaces in the respiratory tract via the indoor environment. It is not easy to define infection, but at present, it will be judged that the number of virus RNA copies exceed the detection limit of PCR. That is, even in the numerical model, it is necessary to predict the virus replication on mucosal epithelial tissue as the number of virus RNA copies. And thirdly, it is important to develop a viral replication model, that is, a host cell dynamics model integrated with numerical respiratory tract and shift analysis. And finally, applying this integrated numerical method to indoor environmental design aimed at controlling airborne transmission. Concerning the inhalation exposure associated health risk assessment, the accurate prediction of inhaled pollutants concentration at the nose or mouth and that of the adsorption flux in the respiratory tract are important. The former is made possible by the integrated analysis of the indoor shifting and the in silico human model. The latter is possible by integrating the host cell dynamics model into the respiratory tract model in a human body. Host cell dynamics model is well known as a mathematical model for predicting the host cell response as a result of the deposition of virus-laden droplet on the airway mucus and the pioneering research results of integrated indoor shifting and host cell dynamics model in respiratory system have been reported by Dr. Yu Fen's research group. The simple host cell dynamics model is summarized on the left side of this slide, and a comparison with the physiologically based pharmacokinetic models for inhalation exposure of chemical compounds. By applying this mathematical model to airborne transmission analysis, it is possible to quantitatively predict the amount of virus replication in the respiratory tract, that is, the number of virus RNA copies, and this means the probability of infection can be determined by comparing the predicted virus RNA copies with the detection limit of PCR method. Here, I would like to show the series of demonstrative numerical analysis concerning the virus-laden droplet dispersion in an indoor environment and particle inhalation via the nose and deposition onto the tissue surfaces of respiratory tract. This slide shows the animation of Lagrangian virus-laden droplet dispersion analysis in case of the worst-case scenario in which the cough directly reaches the face of uninfected target subject as functions of physical distances of infected subject and target subject and breathing condition of target subject. Breathing conditions here, steady inhalation or transient breathing, do not significantly affect the total amount of inhaled droplet and their deposition distributions in the upper respiratory tract. However, physical distance has a significant impact on the inhalation exposure concentration. This slide shows the results of identifying transient breathing zone and direct inhaled air using inverse problem analysis. When the generation conditions of virus-laden particles cannot be clearly identified, it is well known that the transient breathing cycle have an important influence on inhaled air quality. Upper figures denote the time series of the change in the region of direct inhaled air, and it can be understood the breathing air is transported from the lower region of the human body to the nose along the thermal plume around the human body. Lower figures show the time series of the change in the exhaled air from nose. Exhaled air is relatively high temperature and then transported upward by buoyancy. People are not breathing the air in front of their faces. Therefore, to accurately predict the risk of respiratory infection, predicting the transient inhaled air of uninfected people might be important. This slide shows the analysis results assuming the worst-case scenario in which the cough directly reaches the face of an infected target subject. Virus-laden particles that reach the breathing zone are transported from the nares into the upper airway and partly deposited on the inner wall of the airway and partly transported to the lower respiratory tract. The deposited virus-laden particles on mucus are transported in the direction of the larynx by mucociliary motion. At the same time, the virus infects the host cell and begins to replicate. The time series of the change in number of target susceptible cells, infected cells, and virus RNA copies are obtained by solving the host cell dynamics model. By numerically modeling the mucous transport and diffusion of the SARS-CoV-2, it is possible to reproduce the three-dimensional heterogeneous transmission in the respiratory tract. I would emphasize that this is just a demonstrative analysis and need to be validated with future clinical data. Finally, I would like to introduce one more application example of in silico human model as an air quality and thermal comfort sensor in an indoor environment, and show the numerical procedure for heating, ventilation, and air conditioning control by using this in silico model as the objective function for indoor environmental optimization. In this optimized design method, the analysis of flow, temperature, humidity, and contaminant transfer were coupled with CFD and in silico human model skin. Human thermal comfort is evaluated by some regulatory analysis, and inhalation exposure risk, which is represented by the pollutant concentration in the inhaled air in the respiratory tract, and is precisely analyzed as a feedback parameter for HVAC control. Compared with the conventional HVAC control method using a point value in a room as the representative value, the HVAC control method integrated with in silico human model analysis showed potential for precise indoor environmental quality control for local zones around the human body. That's all for my presentation. Thank you very much.